All right. Hello, everybody. It is great to be here today again. This is the fourth time I'm teaching a class of this, and we're basically going to combine natural language understanding with deep learning. And language understanding, in many ways, is the most interesting manifestation of human intelligence, and deep learning is the best possible set of techniques that we currently have in artificial intelligence. So combining the two, I think, will be intellectually very stimulating and exciting. And today we have a full program. It's going to be light. There's not going to be as much math as there will be in Thursday's lecture, but hopefully we'll get through a bunch of the logistics and motivate you to go through this class for the quarter. So we'll start a little bit by just talking about what NLP is and why language is kind of interesting and unique compared to other kinds of inputs that we might think about in AI, like computer vision or robotics. We'll define what deep learning is at a very cursory high level, and then go through the not so exciting course logistics, though those are super important as well. And then we'll actually talk about why language is so hard for deep learning and really any other AI technique to understand, and then hopefully motivate you with a bunch of applications. And what's fascinating is before deep learning, the years before deep learning, when we taught this class, you were able to build some pretty basic things. Nowadays, your final project could actually be to build a machine translation system, a whole translation system that translates from English to German or something like that, because of these techniques and because of the tools that you'll learn in this class. So, also, in general, for all classes, if you ever have any questions, just raise your hand. That's one of the main advantages of being here. Sorry for the people standing in the back. We have still a little bit of space over there. In general, the videos will be available for this class for all the Stanford students around 2 hours after the class happens. So usually that means over the course of the quarter, people will start to use that availability and just kind of watch the class lecture whenever they want, or maybe not watch it. So it'll be less crowded as we go through the quarter. All right, so what is natural language processing, or as we'll just call it, NLP? It's essentially a field at the intersection of computer science, linguistics, and artificial intelligence, which are also pretty broad general terms, and it can actually be quite debatable what it should be, but one thing that we'll see as our main goal is for computers to process or, scare quotes, understand natural language in order to perform actual tasks. So we don't care that much about them maybe understanding, something, maybe being conscious or stuff like that. None of our concern. We want them to actually do something that's useful for us. And when we say performing tasks, we mean things like make your appointment. You talk to it and it'll make an appointment. It sends out an email automatically to you. Or you want to buy something and you give a speech signal. Or you want to translate so you can communicate with other people in another language, or you want to ask it general questions that are a little harder, and you'll notice all these big companies are here because this is something that most companies care about a lot. Because in the end, language is how we communicate most naturally to other people, so it would be great if we could communicate naturally to a computer as well. Imagine if not just the people who can program can tell computers what to do, but anybody who can talk could tell computers what to do. It would be a pretty major change in the world. And the reason we put scare quotes around understand is that really when you want to be snarky or cynical, the computers don't understand anything. And fully understanding and even representing the meaning of language and even defining what the meaning actually is and so on is an incredibly difficult undertaking in and of itself. And so in many ways, you could think of perfect language understanding as being AI complete in the sense that you have to understand all the other AI tasks, like robotics. What does it mean to run? Well, if you can't really run, do you really have an understanding of what it means to run? What does green mean, or a tree? What does that really mean if you can't see it? So now you have to visual understanding, robotics, and motor cortex understanding. If you want to talk about social relationships, can you really have them without understanding global context of people and so on? So language touches all these other areas of intelligence as we communicate about them. And so really, we're not going to even attempt to capture that in all its glory. What we do have are some very concrete task levels and levels of representation in NLP. And they start with something as simple as speech. And in phonology, we're going to try to just understand from a speech signal, what does it mean in actual written text. OCR, optical character recognition or tokenization, is when we read something, can we actually get concrete characters out at the end from maybe handwritten writing or just printed out sheets. Then where it gets more interesting is in morphological analysis, where we try to understand how words are formed. We can call them morphemes. For instance, a suffix and a prefix can be combined and change the meaning of a word. You have usually a stem of a word and so on. Where we're really much more focused in this class are on the syntactic and semantic levels. So syntax, just trying to understand grammatical structures, how are words combined, are certain phrases maybe part of another phrase. So if I say, the girl saw the boy with the binoculars, what does that mean? Is with the binoculars, is the boy holding binoculars, or is the girl using the binoculars to look at the boy? So it's unclear, and maybe you need to have contextual knowledge or visual knowledge to disambiguate this one. And there are lots of other ones that are obvious to us, like the boy eats the spaghetti with a fork versus the spaghetti with the meatballs. So now this is a so-called prepositional attachment ambiguity. For us, it's obvious that when it's the spaghetti with the meatballs that there's a certain type of spaghetti, and eating spaghetti with a fork means the fork and with the fork modifies how you're eating the spaghetti, but to a computer that might not be clear. So those are questions of syntax, and in some cases they actually connect to semantics. Knowing the semantics of eating and spaghetti and a fork and so on will help you disambiguate that grammatical structure as well. Semantics is really the most interesting part of language. It's essentially the study of the meaning. And there are a lot of different kinds of semantics that we can look at, and we'll, in deep learning, and using our deep learning lens to look at NLP, we'll actually have a very specific way of representing meaning, which we'll get to in a couple of slides. Once we understand the meaning and grammatical structure of single sentences, which syntax and semantics are mostly focused on, we can then go and try to understand a whole discourse. And pragmatics, where we actually want to understand this sentence in connection to all the previous sentences that might be in a dialogue. And as you'll see, this will be very useful if you want to build, for instance, a bot, and you have things like anaphoras or co-references, where you say, Mr. Obama went to the White House, and then he walked over to the South Lawn, or something like that. Now, the he refers to Obama, and understanding and tracking that through a longer, complex discourse is what we would do in the last level in pragmatics. But in many ways, just trying to get through those two is going to be enough, so we won't be focused too much on pragmatics in this class or on discourse processing. So there will be a lot of different kinds of applications, and in many ways you'll actually be able to map these applications to these different linguistic levels. And they'll start with the simplest thing that you can just do on single words. Spell checking, keyword search, finding synonyms, things where you just need to look at a single word and something useful happens. And then the next level, and we'll fortunately be able to cover pretty much all of these levels in this class, is a little harder, but not that much harder. We think currently we can solve them usually quite well. And when we mean that, we never mean in all its complexity. You'll almost always find counterexamples for any AI system. In fact, you can almost by definition say, if it's 100% accurate, it's probably not AI, because you can find very fixed rules for it. So there's usually, at the best, you can hope for something like 98% or so in accuracy on any of the tasks we'll look at. But these kinds of tasks in the middle here, we're able to do quite well. And that is, for instance, extracting information from websites. Imagine you want to build a product catalog, but you just have some crawled websites. You want to extract product prices and locations or whatever. You might want to, if you do algorithmic trading, you might want to go through news articles and extract company names and see if their CEO just got fired and probably sell that stock and things like that. In terms of just extracting structured information from such unstructured text, we're pretty good at that. And we can also classify longer documents very accurately. So for instance, you might want to say, is this article overall positive or negative about this company? If it's positive, maybe that's one of the many signals you might want to use to trade the company that's the main focus of this article. You can also think about classifying reading levels. So somebody gives you a potential new assignment for third graders. You want to say, is this probably a good assignment or not, given the various words that are being used? And again, you can classify that quite accurately. Then where it gets really interesting and really hard as well is in the last category for tasks that aren't just a single category, like classification outputs, or just extract certain phrases or inputs from a document, but actually generate an entire sentence. So machine translation is a really great test bed for both deep learning systems as well as for generally thinking about NLP. We can actually we have made as a field a lot of progress thanks to deep learning in machine translation systems. It used to be that you have to have 200 plus people work for several years in some major company to actually get a reasonable machine translation system out the door and have people really use it. Now a handful of people can build at least the algorithms that are equivalent to such a system that used to take hundreds of people multiple years. Then, of course, having actual data sets to train the model is a different story, and you'll see that struggle. Part of the reason machine translation made so much progress is because we have a lot of data. And a lot of these algorithms that we have are data hungry, which also creates an inevitable complexity for you as students of this class, because in any of the larger projects that you want to engage with, and the problem sets, at some point, the data sets have to be a minimum size for you to be able to train anything that's useful. And whenever we have to train a lot, it means it will take some time, and that means you can't do it at the last minute. And so we'll try to reflect that in some late days and so on, but there's a certain minimum set of sort of looking forward that you'll have to do to be successfully training these kinds of models. Spoken dialogue systems, also super interesting, and one of the tasks I'm the most excited about these days is complex question answering. Being able to really ask any kind of question to an algorithm, and it'll be able to either reason over a database to give you the answer, like how many companies have over this revenue and we sold something to in the last 3 quarters. And then you now go to a database and you understand what I meant and actually extract that from a database, or just saying, what was the name of the daughter of the president 3 presidents ago? Pretty hard stuff for a computer to really understand and be able to answer that question. And I think it's question answering really tackles a lot of different aspects of natural language processing. All right, now I think NLP is exciting because it spans that whole range from being connected to thought and intelligence and some pretty fundamental things that make us human. But on the other side of the spectrum, it's also just incredibly useful. You probably will have a higher salary if you successfully finish this class and you're actually in that field. And a lot of companies make a lot of money and impact a lot of different industries and people through that. So search and online advertisement are 2 of the probably biggest aspects of this. Search both in written and in spoken language now. You can talk to your phone these days. Online advertisement, of course, what enabled some very, very large companies in the Valley to make a lot of money and then build a lot more cool AI afterwards. Translation, again, super impactful. Sentiment analysis for marketing and financial trading. We see speech recognition now being actually used in a lot of real applications. And currently very exciting for a lot of people, chatbots, dialogue agents to automate a lot of customer support. That itself is also a billion-dollar industry. Everybody calls and has some problems with some companies all the time. They want to ideally not have people sit there and manually solve those problems, but automatically do that. All right, any questions about the tasks, the levels, the problems we want to tackle? Yep.
You skipped over controlling stuff. What did you mean by that? Because the second to last bullet.
So in the end, you want to not just talk to, for instance, a service agent. You say, oh, my package failed. I want to get a replacement, or can you replace this part? And then If you're purely in NLP land, you might say, sure, we'd be happy to help. We'll send you a replacement. And that's it. And then nothing happens. So of course, if you actually had a real dialogue agent that was successful, it would have to then connect to actually do something. Or in much simpler terms, like you want to say, Alexa, turn off the living room lights. So that's one thing, and then it turns off the lights. In more complex sort of service scenarios, you might want to actually then start a purchase order, print a purchase slip, talk to the logistics office and so on, and then have something actually be shipped. And understanding how those actions relate to the things you say is a pretty complex problem. Yeah.
Can you explain a bit more about the online advertising matching and how you do that?
Okay. Can I talk a little bit more about the online advertisement? So I'm not going to go into too many details, but basically, if you understand what a document is about, you'll be able to match better what advertisements you should show on that web document. And deep learning will help you to usually better understand both what is being asked for and what the websites actually say where you want to show the advertisement. And so that's just like one aspect. Great. So what's so special about human language? There are other AI classes out there, like computer vision, for instance. And I love computer vision. There are actually lots of interesting connections. One of the major differences is that especially human language is a system that is specifically constructed by people to convey a specific meaning. And in comparison to vision or biology and things like that, it's not an environmental signal. It's actually something that we create deliberately. And somewhat amazingly, we're using an encoding with language. Language is essentially an encoding that little kids can learn very quickly and that changes also very quickly. So some people like to call it a science, but in many ways a science is to try to understand the natural world. In language, you might have some teenagers say YOLO, and now you have to scramble and try to update your system. Or they might say lol without laughing out loud, but they still just conveyed some kind of meaning. And so you want to be able to adapt very quickly to that, and it's a tough problem because language continues to change. And one tricky bit that we'll start to tackle, and we have a specific way of tackling in deep learning, is that pretty much most of language is very discrete, and in that way we mean symbolic or categorical, in that we have specific words. Even though when I talk or when I write, there's usually some kind of continuum, in the end, we assume that there's a better, higher reliability when we communicate with very discrete signals that we call words. And in many ways, symbols, which have been the traditional way of looking at AI and reasoning and logic and so on, are clearly a fundamental part of natural language. And what's tricky is we can often have different instantiations of these signals. So we have sound, we can have gestures, and sign language, and we can have written language, and so on. And they all essentially can mean the same thing, but it's always something discrete. On the other hand, our brain encoding doesn't have a discrete signal in it. There's no single point where that discrete aspect is the concept for tree. In the end, our brain has a lot of very continuous activations when we try to say something or when we think of a new concept. And when we communicate that signal, speech will also be continuous. And so for many, many years, traditional natural language processing algorithms use discrete kinds of representations. But when you have 100,000 words in your vocabulary and you try to run any kind of machine learning algorithm over it, you'll run into a lot of issues like sparsity, where you see certain words only once and then you can't really learn from that example. And so in our case, we'll explore representing everything in a continuous kind of encoding or a continuous representation, which we'll often call a vector or just a list of numbers. Okay, so that's natural language processing in a very coarse first approximation. Now, what's deep learning? Again, you'll appreciate the term a lot more in the next couple of weeks. But in some ways, we'll start with it's just a subfield of machine learning, and currently a subfield that is growing more and more. 4 years ago, It was a small subfield, maybe 20, 30%. Now when you go to an AI or machine learning conference, it feels more like it's 80 or 90%. It's really taken over most of the AI sub-areas, not just in natural language processing, but a lot of other ones. And what makes it so special? To understand why it's so exciting, we have to look briefly at what traditional machine learning used to do. And that was the majority of time was spent trying to have humans or graduate students design representations and input features to solve certain problems. So here, for instance, we can see a couple of features that were designed for a named entity recognizer. Named entities are specific nouns such as locations or people names or organization names like company names and so on. And you want to just extract them and say, this is a person name, this is a company name. And you'll basically see here a couple of simple things like the current word, of course, is important. If it's John, it's very likely a person. And then people actually came up with, well, if we know John is a person and Jane is a person and so on, why don't we just have a list of all people's names? And then we manually just curate that list. And then whenever there's a foreign name, it fails, but you know, it's a good approximation to start with, and so on. So you'll see a lot of these kinds of features. You have word shapes, like is the first character capitalized, and then all the other characters are not capitalized, or are they all capitalized, and so on. And you basically look at all your errors, and we sometimes jokingly call it graduate student ascent. The graduate students look at it and keep trying to figure out how to improve their system. And in the end, they would write a paper about how their machine learning is optimizing all these weights for those features. But when you looked at how they actually spent their time, it was really the majority of just describing the problem into these features. And then when you look at the papers, it was often about the learning algorithm, but the learning algorithm could either be the state of the art or 20% lower than state of the art, depending on the features. So that was basically a huge issue for machine learning in practice. And what is now exciting is that with deep learning, we can actually try to capture that whole space from start to finish with ideally as raw of an input as possible. So what is deep learning now in contrast to this standard machine learning approach? In many ways, we want to learn the representations, these features, as part of our learning algorithm. So deep learning will attempt to learn multiple levels of these representations. And what does that mean? Well, ideally, we have as raw of an input as possible. So the raw inputs could be just pixels. They could be characters. In fact, we can now have machine translation systems that literally just look at a sequence of characters in one language, and they learn to output a different sequence of characters in another language. They don't even have a sense of what a word is, and they're still able to translate quite accurately. So in many ways, it started with sound and pixels. So instead of saying, I want to classify this cat by finding a whisker and finding eyes and a tail and some legs, you just say, here are a bunch of pixels. These pixels mean cat. These pixels mean not a cat. And you learn through successively deeper layers that maybe some pixels combine to be edges and certain edges combine to be textures and patterns and so on. And in the end, your final output, H4 here, is cat, yes or no. But of course, this is only how it started. And nowadays, we don't just have this fixed kind of layer and have the same kind of layer every time for a fixed input. Language doesn't have a fixed input length. We can't just, like we can with images, resize all sentences to be exactly 20 words. Right? It doesn't work. So it's just how it started, and one of the reasons why it's called deep. But in many ways, it actually started also with a lot of different kinds of techniques. Initially, deep learning encompassed both different kinds of undirected graphical models, and there's a whole lecture on graphical models, though it doesn't take as much of a deep learning approach here at Stanford. Nowadays, when people say deep learning, they almost always mean neural networks and different kinds of neural networks. This is essentially now the dominant family in deep learning. And you could be snarky and just say, well, it's just clever terminology. Neural sounds cooler than stacked logistic regression units. But again, if you want to be snarky, you could just say, well, that is also it. So if you understand logistic regression, you'll already understand one of the major pieces of deep learning. So actually, let me ask a show of hands here. Who knows logistic regression really well? All right, good. You'll have a good time. So one one of the interesting new things that is coming up over the last couple of weeks is actually to maybe rename all of deep learning into differentiable programming. And it's a clever idea, and if you know already a little bit about TensorFlow, you might understand this. I can't go into all the details, but we'll have lectures on how you actually program. We'll have a specific lecture on just TensorFlow, which is the main framework that we'll use for most of the problem sets. And if you think about it, it's actually quite a clever term, and it'll become clearer later of why that might be a better term than deep learning. In general, we will not take a historical approach. When these videos are online, or there are certain people out there who have invented something in the 1980s, and then the computers were too slow, nobody used it. They might get upset that we're not mentioning their name. So we're sorry. There's just a very long history. It's just only in the last couple of years that these techniques have started to work, and we'll focus on the things that work, and in particular work well for natural language processing. So there's some really great work here by Jürgen Schmidhuber on an overview of the whole history of the field. It's a very long and very detailed overview, starting very early, before you could have even trained most of these models, or any of the ones that we're currently looking at. But that is not the approach we're going to take. All right, now why are we looking at deep learning and not spending any more time on the traditional NLP techniques, of which there were many, and last year was the first year where we actually combined a class that I had been teaching on deep learning for NLP for 2 years before with the traditional NLP class, and we've switched entirely to deep learning methods. And essentially, it's that problem that I mentioned already with the features. Not only did it take graduate students and other experts a long time to come up with them, but in many cases, they're overspecified and incomplete at the same time. So sometimes they made some very specific rules, but then contextually, they weren't quite right. And I'll come up with examples later to show you how they're almost always incomplete. Again, the YOLO and LOL example are just two, and there are many others. Then, in contrast, the learned features that you'll be able to eventually program yourself in this class are going to be much easier to adapt, and with enough training data, they're very fast to learn and much more general. And deep learning provides, in general, a very flexible and universal framework for also representing not just the meaning of words, but also visual information and other kind of extra-linguistic information. So in the end, you can use the same model family in some cases to understand images as well as understand text. And that's pretty amazing and pretty general, and that was something that was just impossible in prior natural language processing algorithms. And what's also very exciting, we'll be able to look at both unsupervised and supervised models in deep learning. And again, it's a very general frame, and eventually almost like a way of thinking about most AI problems. So why has this happened? And this is about as much of the history we will do in the class, but it's kind of interesting to at least mention it. So in 2010, deep learning techniques started outperforming a lot of the traditional machine learning techniques, and there are really three major reasons of why that was the case. The first one is we have more training data. If you don't sit there manually and you think of all the positive and negative words, or all the ways you might write down a company name with capitalization and so on, when you can't do that manually and you learn everything from just the text, you need to have a lot of text to see all these examples and have the algorithm actually be able to capture that. Now, deep learning algorithms also have a much higher capacity. They have a lot of parameters. Again, that's why they're sometimes slower to train. But they really benefit from having larger training data sets that we now have with computers and hardware costs and storage costs and so on going down. Then another major advancement, especially for vision, but also for speech, and increasingly so for natural language understanding too, are faster machines, and especially multi-core machines. To some degree CPUs, but for the most part GPUs. One of the reasons NVIDIA's stock is rising like crazy right now is that everybody needs GPUs to train these models very, very quickly. And in fact, we'll try to also help you out with compute infrastructure, because we know it's a really tough problem if you want to train more exciting models. So faster machines, a lot of the computation that you'll do will boil down to matrix multiplications. And matrix multiplications, fortunately, can be parallelized, right? Every row that you multiply with a column vector can be parallelized as you compute it, and that is really, really nice if you have 2,000 cores on a GPU. And you can basically compute that entire matrix multiplication in parallel. And then there's an often overlooked aspect, but the third reason of why this has worked better now versus 10 years ago, or even just 7 or 8 years ago, is that we also have a lot of new kinds of models, algorithms, and ideas around deep learning. We basically can now think of all these models as end-to-end trainable. And end-to-end trainable might be another really good term that might take over compared to just deep learning. End-to-end means we have some raw input, we have something we really care about, and we're just going to try to make the model predict what we care about based on that raw input. So instead of saying I can extract a lot of features of who is talking and which objects are they talking about and what's the grammatical structure of the sentence and what are the organizations and people names, if in the end I just want to predict this is the answer to the question, I'm going to try to have a data set that goes from the answer to the question all the way back to the raw input that you started out with. So end-to-end trainable systems are great. As you have these end-to-end trainable systems, all the intermediate layers of representation, and it's a little of a bit of a fuzzy term, we'll understand much better what it means even in this lecture, will be learned, and they're very flexibly learned. Also, we can represent the context a lot better, both visual context, but also other linguistic context. And we can regularize and optimize these models a lot better. And you'll, fortunately, won't have to go into too many details of which optimizers you use. A lot of the frameworks that we'll use will just do that for you. But it's good to know that if you just use SGD, especially for some NLP applications, it would not just work as well. SGD is stochastic gradient descent, which is what you would usually use if you train like logistic regression and things like that. So all of those three things combined essentially led to an increase in performance, first in speech recognition, then in computer vision, and now also in natural language processing. So the first major breakthrough in speech was actually by George Stahl in 2010, who used a context-dependent pre-trained deep neural network for large vocabulary speech recognition. That was the title of the paper, and had a really incredible drop in the so-called word error rate, which is the main metric you use to evaluate speech recognition. And in comparison, he had many fewer features than all the previous traditional models had used. And at the time, it only took short samples and then spit out single phonemes, or in some cases, single words. It didn't actually learn the entire problem. And so there's still, in the first iteration, there's still actually some traditional other machine learning methods that were used, like hidden Markov models and so on. But eventually, now we have completely end-to-end trainable speech systems too. But this is how it started in 2010. And then in 2012, one of the major breakthrough papers in deep learning came out, as authored by Alex Krzyzewski and Ilya Sutskever and Jeff Hinton. Jeff Hinton, kind of the godfather of deep learning. He's been working on this for several decades, even during times when it wasn't quite as hip and would maybe only get a class of 10 people and not of 500. But he worked on this for several decades and really made a lot of progress, and eventually came out with this paper. And this is what I meant with the different layers in a neural network. It looked at just pixels, and it was able to classify a lot of different kinds of categories, even fine-grained kind of visual categories like this, which in some cases you might not be able to do, or I certainly would not have identified a rough gross myself. But what's interesting, and these are the layers and visualizations of what I mentioned with H1, H2, and H3 in the first slide on deep learning. When you looked at just raw pixels, it would learn that pixels would combine to little edges and color blobs. And then when you combine these edges and color blobs, you would get interesting textures and more complex, but still very simple shapes. And then as you go to layer 3, you would start to observe smaller parts of objects. And it would learn all of these features automatically. Now, of course, in language, we sadly don't have such a nice visualization of, oh, you meant running, and you kind of combine the ing with something. It doesn't work like that for us, so we won't have as many beautiful visualizations in natural language processing and deep learning, but we'll actually have some. And we'll also help you try to understand what these models are doing a little bit throughout the class. All right, now on to some less exciting course logistics. So I'm the main instructor. Hello. This is my first year as an adjunct professor. Before that, I was just a visiting lecturer for 3 years. Very excited to be here. Then we'll have 2 wonderful head TAs. Maybe they can stand up for a second and wave. So we have Kevin Clark and Abigail C. Abby. They'll also actually give some of the lectures, which I'm happy about. And thanks. And then we have a lot of other wonderful TAs, which you'll meet throughout the course of the quarter. I don't know if we, you can, let's wave and say hello. All right, there are some waves. We might get even more TAs because the class has increased some more. Class lecture, you figured that one out already. We're here. We'll be here every Tuesday and Thursday. Videos are online 2 hours after the class. The course website should have most of the information that you need. The office hours, I'm a big believer in office hours. I'll mention it a couple more times today. You should come to office hours as much as you can. Sadly, with such a large class, it's very hard to optimize office hours in a way that there's no wait time. So we'll try something slightly improved, hopefully, compared to last year, where we'll have fewer office hours but with more TAs, so that we can have a higher throughput. So we'll have probably 4 or 5 office hours that are 2 hours and have like 4 or 5 TAs each in them, so that hopefully the wait time is shorter. We'll use Piazza as most classes now do. You can sign up on that, sign up for that through the website, and there's a link. I'll try my best to upload all the slides before each lecture, so if you want to print them out, you can do that and take some notes. Any questions around any of those logistics? Yeah?
Is there a difference between courses?
No.
It's just kind of up to you. We don't distinguish between that. Yeah. The question was, is there a difference between 3 and 4 credits? And there isn't. All right, prerequisites. So it's pretty important for you to have a good time or not. So all the assignments will be in Python. Most of you will probably know Python. Actually, show of hands, who has programmed in Python? Good, awesome. Okay, for those who haven't, and there are some hands that were not raised, we try to be as inclusive as possible. So we'll have a Python refresh session. Actually, a couple days after we release the first problem set, which will be this Thursday. So if in the first week you just struggle too much and you can't really tackle the problem set because you're missing Python, we'll have a refresh session for Python at this time, January 19th, which is a Friday. You also will need to know multivariate calculus and linear algebra. Those are some simple math equivalent classes. You'll need basic probability and statistics. And ideally, you also have the fundamentals of machine learning. So you've taken already a precursor to this class that teaches sort of traditional machine learning methods and AI methods like 229 or 221. In particular, you'll have a much easier time if you know loss functions, you know how to take simple derivatives, and you know how to perform optimization with gradient descent. Now, in general, when we look at course evaluations, as with any law of large numbers, there's going to be some kind of normal distribution. And especially the people who really, really are going to dislike this class by the end are the ones who don't have a lot of these prerequisites, and in combination probably don't come to office hours very much. And so, especially last year when the class kind of blew up and we combined, the deep learning class and the traditional LNP class, some students really struggled. And where they struggled with organization issues, I think we'll be able to improve them this year a lot. But if, in general, this is a very hard graduate level class, and it will take a lot of time. It probably will take more time than a lot of other classes. So if this is like your super busy quarter of like 10 different classes, this is probably not a good good one as like one to add as a 10th class. In general, I really care. I actually don't get paid. I just do this for fun, so I do it because I really care about the students. So if you feel like somebody doesn't care, just go and talk to them. Come to office hours. That's the #1 thing. This is one of the ones that pained me the most in terms of teaching evaluations and reading them. Is like thinking that the instructors don't care. We care a lot, and if you come to office hours, you'll see it. And we also have a lot of other ones that say the exact opposite. So my interpretation, but it's a latent variable we don't really know, is that those folks came to office hours and those folks did not come to office hours. So come to office hours as much as you can and give us feedback. If there's something not clear, tell us. Fortunately, this year, all the problem sets have been done before. So we don't have to have like crazy new problem sets with everything new in TensorFlow and so on. So most of the bugs should be ironed out in all the different problem sets. What we found in office hours often, and that's what I mean with off-cycle, there are going to be office hours that have 100 people who all want to talk to me in 2 hours, which never happens. So then my office hour becomes like 6 hours. And I'll stay there till midnight, which I will, and especially as the projects will go on. But it also means some people who came half an hour into it will then have to wait for 5 hours. And there's just like, I don't know what else to do other than staying as long as we need to finish everything. And then the next week, nobody shows up. There's like 2 people come, and after half an hour, I'm just like answering emails. So if you want to have more time, think about the off cycles, as in the problem set was just submitted. Everybody's like, wait, finally, 1 week of no problem sets. Those are the weeks that you'll have a lot more time in the office hours, and you'll get a lot more one-on-one time with the TAs and with me. All right. So what do we hope to teach or hope that you learn? #1. Any questions around the other organizational stuff? Yeah?
What kind of computational resources are we going to have?
Great question. What kinds of computational resources you're going to have? So we'll have a list on the website where we'll list like the various rice and corn and rye and other foods kind of named clusters that we'll have. So you have those. And then we also work with Microsoft Azure to get, I think, $80,000 worth of credits or so to distribute to students. And you can basically run some experiments, especially for the final project on those. Good question. And that's also something that's tricky, right? In many ways, you can run an experiment on a smaller machine that was slower, and it's fine if you have 3 days extra. If you then all of a sudden you didn't start your project in time, and now you need to run that same experiment in 12 hours, you could also do that, but now it costs you $1,000. And so ideally, you just don't end up in that situation because we can't like pay for all those resources if they start too late. So this whole computing resources is a tricky bit in deep learning in general, and I guess part of the learning experience of this class is learning how to deal with limited compute resources. Yeah.
Will the homework assignments also, on occasion, require a lot of
the first couple of homework assignments and problem sets will not require you to use some crazy big cluster. We're trying to, they're more educational and less like, oh, I have to build the whole system. All right. So what do we hope to teach and that you'll learn? Understanding of and ability to use effective modern methods of deep learning. We'll start with the basics. And I mentioned here understanding of. So you're going to have to go through a lot of derivatives. And in this plot here, there will be around a quarter of the people who say, I know how to take derivatives, this is super boring, and I'm sorry to bore those people. But there will also be a quarter of people who are like, I thought I knew how to take derivatives, but it turns out when you have a gigantic neural network, it's really, really complicated, and I'm kind of lost, and the class is way too much and too fast, and I don't get it. And there's going to be 50% of you who are just like, this is good speed, they're teaching it, I'm getting it, and life is good. So in general, the understanding actually does boil down a lot to derivatives, and having at least once gone through it will take out all the, oh, this is kind of black magic. I just putting something into a framework and cool things happen, and you actually really understand it. And it's really an understanding. You could not understand all the details and probably still use it fine. But this is not like vocational school to just be a hacker. Like, this is not deep learning for hackers, but like actual graduate level deep learning class. So I think it's good to actually understand and demystify it all by at least for a couple of lectures and a couple of problem sets, really dig into the details of the math. And then once you've passed through that and passed the midterm, the second half is mostly about how to actually hack up cool things and really build NLP systems. Big picture understanding of human language. So we'll actually look at a lot of different applications. I already mentioned a couple, like trying to understand grammatical structure, understanding co-reference. He and Obama and the president and Barack all meant the same thing, things like that. Trying to understand machine translation and the details, and in a few cases also sort of what makes deep learning so special for these uses. And then understanding of and ability to build actual systems. And we'll use TensorFlow. There are actually a lot of other frameworks out there, and I'll talk about that a little bit later, but in our class, we'll use TensorFlow for the most part, and we'll actually want you to be able to really build systems and models that can identify similar words, that can understand syntactic structure, translate, identify entities, do question answering, and understand sentences to some degree. All right, grading policy. Not very exciting. Don't have to talk about it that much. You'll have assignments. One thing that came up before is that in the end, we'll design the assignments such that you should be able to solve them with a reasonable amount of time. And we'll try to give you the gradient checks and things like that so you can almost know how well you will do before you submit it. And so in many ways, most people will do pretty well on that. And so then the other two parts are sort of the major differentiator in terms of grades. The midterm is the one time where you can't just like, spend many, many hours on or ask other people for help and so on. You really have to just be able to do the math very quickly and have some memorization capabilities and so on. And we actually have a bell curve there. It's not going to be like most everybody has over 95% like in the assignments. And then the final projects is something that we've thought about a lot between the TAs and sort of used learnings from previous years. And basically, we'll have a much improved problem set 4. And we also encourage you to use teams. So now is the time to think about who you might want to work with for your project. It's much easier, and you can do more for both problem set 4 as well as for the final project if you have a partner. If you do a final project, you have to have a mentor, and you have to get sign-off from Abby, Kevin, or me. So the default for most people will really be to just focus on the 4th problem set. I'll talk a little bit more about that later. Final poster session is essentially your final, so you really have to be there. We'll announce the date in the next couple of days. Want to make sure we coordinate with other classes and reduce the overlap between other finals that you guys might have. But it's kind of your final, so you really want to present it. It's actually going to be fun. We'll have probably a prize again. You might win like a GPU or something if we get that organized. And you'll learn about a lot of cool projects. And the projects really astonish me in many cases. There's some really, really cool projects. You can look at my Twitter feed, for instance, from like last year around this, around the time of end of March or April. And some of these projects become actual like conference paper submissions in the top AI conferences. It's really quite incredible what some of you will be able to generate here after just 1 quarter of this class. Late policy, again, lots of computation. We'll give you 3 late days. Hopefully, you don't use them all up in the first 2 problem sets, so you have some more later. We can't, unfortunately, accept them after 3 late days because we want to show the solutions, and then it's kind of a struggle of how much do you help the people who are super late versus the people who submit on time but want to see the answers. So we'll basically give you at most 3 late days, and then we'll usually release the solutions. And again, just understand all your collaboration policies and so on in the honor code. All right, some more on the problem sets. The beginning problem sets are hard because you need to do a lot of math. And if you're not as smooth with all your derivatives, it'll be hard for that reason. The end of the class will be hard because in the end, you actually need to implement almost recent research papers, like papers from last year or this year, you'll be able to implement. And those are the papers that Google and Facebook and Salesforce and Microsoft and so on, like all these big companies and also all the good universities like Stanford and Berkeley and so on, they publish like hot off the press. In most cases, you'll be able to program them and actually implement those methods. But it's still a lot of work. You have theory, the capabilities, but it's going to require a lot of work. And in many ways, it's going to be open-ended. So both the project and ps224, and you can choose, again, which one you want to take, are pretty open-ended. We'll start with just pure Python in problem set 1 so that you really understand, can look into all the details. Nothing is automated, as it will be then in problem set 2 and 3, which will be in TensorFlow. It's a great library for putting together neural networks and then actually do all that math you had to so painstakingly learn and do manually in the class. Eventually, all of that will be automated. But at least you'll know what is being automated and have a better understanding. And it's actually an interesting choice to use TensorFlow. In many ways, it's the most popular deep learning framework, especially around practitioners who apply it in companies and so on, and also for some researchers. But to be honest, most people in my research group and most people I know have now switched to PyTorch. It's actually even more flexible, and especially for research, it's even better. You can more easily break outside of the convex hull of known methods and do something really, really novel. But we don't want to switch around all the problem sets. And TensorFlow is still the most popular library, the most widely used one. And it's sufficient for most of the things you need to learn and want to do in the class. So we'll stick to TensorFlow. There are a lot of other libraries out there, some academic ones. Several of them have big company support behind them. It's kind of an interesting battle of open source libraries these days. All right, any questions around problem sets? Yeah.
If we are officially taking the course, do we still do homework, or we have to turn it in at a certain date?
If you're auditing the class and you're not officially taking the class, we will not grade your homework. Sorry. We have 530 people we want to grade and have to grade on certain times. The TAs by the end of this class will semi-love-hate me for all the work I put on them. And so we just can't grade people who aren't officially enrolled. But, and again, most cases, you can differentiate, you can check your gradients, you can look at the results. We can tell you, like, you should be getting this accuracy if you're doing it right. And if you get it, unless you have some odd combination of fortunate bugs that, on the one hand, it doesn't work. On the other hand, your evaluation script is wrong, too. So it's rare to get it to good accuracy and still be far off. All right. So a big part of the class, 35% of the whole grade, is the final problem set 4 and the final the final project. So for many people who love the class the most, the final project was what they got the most out of. Some people put that on their CV for the rest of their lives. Some people submit papers to the 2 top AI conferences like ICML or NIPS, Neural Information Processing Systems, based on their class project, and it follows them throughout their career. It's a really cool opportunity to build a deep learning model from scratch, but it's also incredibly hard. And there are, in some cases, really sad stories where, like, the most ambitious students had a project that was a little too ambitious, and they spent a lot of time pre-processing. They're like, oh, I'm going to take this website data, and then I'm going to do something cool with deep learning to predict something. And then they spend 80% of their time just writing web crawler. They get blocked, they write a load balancer and have 5 machines that try to get the website, and they do all this crazy amount of work. And in the end, they have like 1 week to do something with deep learning and NLP. And that's the part that we're going to have to grade. So we're going to make it a little bit better and give you some leeway for trying to be creative and create like a completely new kind of problem, maybe a new kind of data set and so on. But in the end, the class is about deep learning and NLP, so you have to spend a significant portion of the final project on that. And so we're trying our best to help and also give guidance. And again, you have to have a sign-off to do the final project. My hunch is the problem set 4 is a great default for most everybody in the class. We're improving it a lot compared to last year, and we're actually going to release it much earlier. Especially for the reason that you want to understand and have full knowledge of whether you want to do a final project or problem set 4. And if you have to do that before you know exactly what problem set 4 looks like, you have incomplete information. So we're going to release problem set 4 2 weeks before the final project proposal is due, which is roughly after pset 2 is due. So that way you'll have 2 weeks. You can look at pset 4, which is going to be a really interesting question answering problem over the Stanford question answering data set. Very cool data set. All the top companies have a leaderboard and they're submitting their numbers. And if you do well on that, I can guarantee you job offers will fly in. It's a very popular data set. And we've improved it. It's much easier, and you won't have to spend the first half of your project just pre-processing a data set, crawling it, tokenizing it, and so on. Most of that will be done for you. So it's a really good default for most people, but it's also open-ended. We're going to make it easier. You're going to have some starter code again and things like that. But then in the end, we're probably going to, or we will for sure have a leaderboard, and everybody will submit their system and look at the actual accuracy that you'll get in your system. How accurately can your system actually answer questions? And it will be a leaderboard. And the bottom of the leaderboard is you just ran the starter code of sorts and made some minor modifications. And then top of the leaderboard will be really impressive people who basically will have started halfway through the class and are going to hack and do some really impressive work. So those are the two things. If you do your own project, you can use any language or framework that you want. You could go crazy and implement it in raw C++. Don't do that. I'm going to spend a lot of time debugging your derivatives. But in theory, you can do anything you want. And again, we encourage the teams, so start finding a partner soon. We'll have like a Piazza special section where you can talk to people if you're online and you're not here, or if you're here. It's good to have your partner fixed early and think about the problems early. And we'll also actually have a couple of default requirements for your final project. Like you have to have your data set ready by the milestone. And this comes from us learning that, again, very ambitious, very cool sounding projects by very smart people end up not being very successful because they spend too much time pre-processing. All right, any questions about pset 4 or final project?
Does pset 4 involve a written paper, poster presentation?
Great question. How is pset 4 different to the final project in terms of the paper and written project? They're actually quite similar in that respect. So in the end, in both cases, you'll have some research papers, and you're going to want to implement them. In pset 4, we're going to give you some help, and Abby has already started some really good work on that. We're going to give you some help and say, this paper here, read the paper, and if you can implement it right away. But if not, here's what that actually means in a way that uses the lingo and the notation that we had in class. But then there are going to be another 5 or 10 other papers, and the more you implement, the better your score will be. And in the end, you're going to describe your final system. What is the model that you use to solve the problem? What's your accuracy? And then we'll give also extra points for clever error analysis and clever visualizations and maybe a cool demo. And so it's pretty open-ended. But in all cases, you're going to have to be at the poster session, describe your model and your score and your errors that you've analyzed and all of that. So the deliverables are pretty much similar.
But is there a paper deliverable for pset 4?
There's no paper deliverable in the sense like an academic research paper. It's just going to be like your final class report for the problem set. All right. So in the remaining 18 minutes or so that we have, right? We have till 5:50. We'll talk a little bit more about fun stuff again. Unless there are any more questions around anything organizational, structure. No. All right, cool. So why is natural language processing hard? Why do we need this whole class even to tackle all of this and these fancy deep learning methods to tackle all the problems? Well, there's a lot of complexity in representing, learning, and using not just language, but also all the other kinds of knowledge that go into language understanding, such as situational, contextual, world, or visual knowledge. And in many ways, the interpretation of language itself will depend on some extra linguistic context. And so one of the major struggles that computer systems have is an ambiguity. So for instance, if I gave the sentence, I made her duck, that can have a lot of interpretations. Does anybody have an idea of what the first interpretation is that comes to their mind?
I compelled her to crouch.
You compelled her to crouch like this. That's right. I made her duck, and something was flying over and didn't hit her. Okay, what else?
Yeah, you cooked a certain duck dinner for.
That's right. You cooked a duck dinner for her.
I crafted something in the shape of a duck and gave it to her notes.
That's exactly right. You actually crafted something that looks like a duck, and then there may be one or two more. I made her duck. No? Yeah?
I guess your interpretation is she had a duck, I made it.
That's right. You actually made the duck that she owned, and it was hers. So that's one. This is kind of a funny, simple example, but those are actually happening in real life too. So for instance, whenever Anne Hathaway, this famous actress who won multiple Oscars, stars in a movie, the reviews come out, and then the stocks for the company Berkshire Hathaway go up all of a sudden. And it's been observed multiple times now since 2011. Whenever Anne Hathaway movie comes out, reviews positive, company stock for Berkshire Hathaway go up. So there are actual financial traders who trade millions of dollars on Hathaway, but it's the wrong Hathaway. And we call it entity disambiguation or resolution, and it's a real issue that happens in real life systems, and there's a lot of money attached to it. Here are some other fun examples where algorithms will struggle with ambiguity. And even once you read it, you might already have a interpretation. But what are the two interpretations that you might come up with here?
Yeah. So one could be the Pope has a baby. It's literally steps.
That's right.
Other could be that baby steps is together.
That's right. So yeah, one is he has a baby and it steps on gaze, and one is Pat's just saying it. I'm sorry. And one is he's making baby steps on it, which is much better. Another one is this one. So that is either a very ferocious tumor that fights pretty well, or he fought back after it and then recovered. So this is a great example of similar to the one I gave of the spaghetti with fork or spaghetti with meatballs, eating them. So what are the two interpretations here?
So either it's the farmer who has the axe, or it's the cow.
That's right. Unfortunately, we all know that it's pretty hard for cows to wield an axe. But for computers, it might not be as easy. And here's the last example. Fortunately, we live in a judicial system still for now, where one is just funny. All right. So basically, ambiguity is a big issue. And as we go through different kinds of linguistic levels, we'll struggle with it in different ways. Now, I said, this is natural language processing with deep learning. So we'll call it, in short, deep NLP, deep natural language processing. And we're basically trying to combine ideas and goals of NLP using representation learning, learning these features automatically, and using deep learning methods to solve them. And throughout the last couple of years, it's now basically been clear that deep learning has improved every single level of linguistic hierarchy, morphology, syntax, semantics, discourse, and pragmatics, and so on, and has also improved all the tools that we use, intermediate tools like extracting entities or understanding grammatical structure or just identifying parts of speech, like is this an adjective or a noun or a verb, and so on, as well as the full end-to-end applications of sentiment analysis, question answering. So I want to just go briefly through with you these couple of applications so you kind of get a sense of where we're going. So the first one is word vectors. And this is what we'll spend most of Thursday and next Tuesday on, is trying to describe the meaning of words. And in our case, this will not be just this discrete entity, and we have 100,000 words, and whenever we see it, we add a point, and then we'll have some weights on those kinds of points. But every word will be represented as a list of numbers. And that list of numbers has only meaning in constellation to all the other words. And what you see here is a visualization, and we'll zoom in a second. It's a visualization as we project these usually 100-dimensional spaces down to 2 dimensions. We'll gain some insights into what is being captured in these vectors. So expect, for instance, might be this list of numbers. Again, usually they'll be 50 to 500 dimensional, and we can't visualize them. But when we project them down to 2 dimensions, we can kind of start to see some patterns emerge. So for instance, the vector of Germany and France, those 2 vectors will actually be quite close to one another, which is kind of intuitive, right? 2 Central European countries. And in many cases, you'll observe that this will come, and this is how we train it, from the context. They appear in similar contexts. Both might appear in the context of being middle, Central European countries, are both part of the European Union, and so on. And Germany and France and Britain are closer than they are to China, for instance. And then in other parts of the space, we'll observe that all the verbs are actually closer to one another. And saying, thinking, and expecting are closer to one another versus, for instance, auxiliary verbs like had, has, and have. And being and different types of being are also close to one another. And again, they'll be appearing in similar contexts. But we only understand this not by just looking at this list of numbers, right? This list of numbers doesn't tell us anything. But the constellation of the words and how far they are from one another is what gives us all this information. And what's amazing is we will learn this kind of meaning just from raw text. So this will be one of the biggest successes of unsupervised deep learning for natural language processing. And you can be actually snarky and say it's not quite deep. It's actually just a single layer. It's actually as flat as you could possibly make a single model. But because it is inspired by a lot of deep learning ideas, and because it'll be step 1 for all the other deep learning models to use these kinds of word vectors, we'll spend a lot of time on them. And they're also good to get started taking derivatives, things like that, and how we train them. What's amazing is we can actually look at the similarities. So we just look at a word in this 100-dimensional space, and we look at what other words are close to it, or in just simple Euclidean distances or things like that. And what's fascinating is the nearest words to frog, for instance, or toad, which is kind of, most people would still know it, and then Litoria becomes a little, more expert knowledge, and then all these various other terms I'm not even going to try to pronounce. And when you look up what they actually mean, it turns out they're actually all different kinds of frogs. So it learned this just by looking at a lot of text. So you take all of Wikipedia, or sometimes Common Crawl, which is an attempt to crawl the entirety of the internet, and we'll actually be able to find all these similarities between words. So everything is a vector, and once we represent things as vectors, we'll also use neural networks to understand grammatical structure. Here's an example of what such a grammatical structure might look like, and it actually comes from the Stanford NLP parser, which is a neural network architecture as well. Here the sentence is, markets have been jolted by concerns about China. And now what this particular syntactic mechanism called dependency tree tells you is, for instance, that jolted is the main verb, and it has a passive noun subject here. It has auxiliary verbs, and so on. They're also passive. It has a noun modifier, such as these concerns here, and the different cases and other noun modifiers of those concerns, and so on. So this is kind of an example of a grammatical structure that we'll learn. And semantics used to be very concrete and very logical. So you might, for instance, in the past, say for a sentence like Mary likes Sue, that likes has this very complex lambda expression. And if you're familiar with lambda calculus and lambda expressions from programming languages, you might see some similarities. It takes any kind of argument here, and then we'll basically replace that argument in here. And in the end, you get this kind of discrete structure of likes M and S. But really, if you don't know what likes means, or that likes is similar to adores or loves or appreciates or whatever it is, you still don't really have a good sense of what that means in terms of actually using it for something. So there's no sense or notion of similarity or the fuzziness of language. And likes m, s has no similarity to loves m, s or anything like that. And in order to describe words with this kind of formalism is a lot of work that's done by experts. And in many cases, it's very brittle. And you might say things like, I like, right? And then like it's missing it. And you have to come up with lots of counterexamples and so on. And then you end up realizing that it's not quite as useful. What's amazing now is with deep learning, everything will be a vector. So you have every word, like all reptiles walk, everything here is a vector. And you just combine different words with a neural network, and we'll learn about that next week, into another vector, and you keep combining vectors. In the end, you just have a classifier, standard machine learning classifier that takes the final vectors of all of these words and just says, are those in a specific relationship? So if all reptiles walk, does that mean that some turtles move? And it'll just give you a probability for whether these two are in a specific relationship, specific logical relationship, like one entails the other, or one is contradictory to the other, or you can't make a distinction, like all reptiles walk and John likes to. Like there's no relationship between the two, but in some cases, all reptiles walk versus some turtles do not move. Those are contradictory. And it turns out everything is going to be a list of numbers. We pipe them through neural networks, and in the end, we can make very accurate classifications about two logical statements. So we can do logical reasoning with neural networks, which is quite surprising. And this is work by Sam Bowman, who was a PhD student here at Stanford in 2014. And we'll see more complex NLP applications like sentiment analysis, where it used to be the case that you'd have to treat the whole sentence as a bag of words, where you ignored the entire word order of the sentence. You just kind of like counted where the words, if the words are in the sentence or not. And then you used to have a curated list of all the positive and negative words. And you say, all right, wonderful, amazing, beautiful, super, and awesome, and so on. These are all my positive words. And then you look at your errors and you realize, oh, but now they're negated. So then you say, all right, well, I'm going to say not a positive word in this list is going to be negative, and not a negative word might be positive. But then you realize that, well, not awesome is actually not quite the same as not good. Not awesome could be like it's still kind of decent, but not good is probably pretty bad. And so then you say, all right, maybe have different sets of adjectives and so on. You do all this manual feature engineering. And again, it will take a while. It's very hard to capture all the different kinds of negation either. So here's a good example I just came up with, like ain't gonna capture everything. Sad smiley, like, unhappy, frustrated smiley face. And that was probably not a rule that the people who are experts would have come up with to correctly capture this type of negation. And so in contrast, there are lots of different models that are using deep learning that will actually learn these kinds of negations. And this was one from my PhD a couple of years ago that actually correctly classified this sentence. So this movie doesn't care about cleverness, wit, or any other kind of intelligent humor. And actually realized that despite having a lot of positive words in here, like humor, intelligent, kind, cleverness, and care, and only one doesn't in the beginning, it still realized this was overall a negative sentence. And we didn't have to define any manual rules around not caring about something. A lot of different positive things will still make it overall negative. It just learned all of that from the data. And some of the super hard and very advanced tasks are question answering, where again, traditionally, you'd have had to spend weeks or months or sometimes years engineering features to capture all the different kinds of world knowledge and other kinds of knowledge. You'd come up with lots of regular expressions, and you say, if X was a president, then you add some modifier temporally that it's not true anymore, and things like that. Look at various features for different WH words, like who, what, where, and when, and so on, and you come up with regular expressions for all the different kinds of questions you might ask. Now we actually have a system that can do question answering on the trivia, like a trivia competition called Quiz Bowl. It's actually a cool project by Jordan Boyd Graber, who's now, I think, in Maryland. I think he just recently moved. But basically, they had just a couple of graduate students build an entire system to learn trivia. And eventually actually have little competitions similar to Jeopardy, and they're able to, the algorithm at this year's NIPS beat, in the competition track beat, and like a set of experts, like 5 different experts who all try to compete against the algorithm. And again, that is just like 5 or 6 people in graduate school and a professor building a system to beat a trivia competition and beat human experts in that. And again, this is sort of the traditional way, like the Jeopardy system that won with the Watson system, that was hundreds of people with traditional machine learning trying to build all the various features to beat Jeopardy, versus one system that learned all of this in a mostly end-to-end fashion with deep learning, can build some incredible systems and do incredibly well. And you can again visualize sort of different answers that this trivia competition might come up with. And what's fascinating is it essentially kind of groups early presidents, for instance, together, and it basically projected all the different facts that you might have about these different entities that you have asked trivia questions about. It projected all of that into just a list of numbers again, into this vector. Another really cool application is in dialogue agents. It's something we won't spend that much time on, but the models that you learn can actually be directly applied to dialogue agents too. So a very simple and successful example of this is the auto replies in your Google Inbox app, where it just sort of says short phrases that might be good default answers to emails. And one of the things we will actually talk a lot about are neural language models, which essentially are very simple sequence models. You have a sequence of words that comes in, and at each time step you try to predict the next word. So for instance, the cat is eating. Most people now would probably do reasonably well in putting a high probability on things like the mouse or their food or something simple. And most people would not say chair, right? Or some crazy thing like the verb, like running. That would be very low probability, and language models will just basically try to predict the next word. It's a very useful and fundamental task, and we'll spend at least 1 or 2 lectures on that. And it's also a great excuse to talk about neural sequence models. And of course, language to us is often going to be a sequence of words, which will be a sequence of vectors, and we'll want to be able to do very well in sequence prediction kinds of problems. All right, the last task, machine translation. Again, it's one of the fundamental tasks. Used to be hundreds of people being required to work on these problems. And hundreds of people, when they have to work on a problem, will often come up with different solutions. So we have lots of different MT systems, machine translation systems, that try to have various different ways of translating. Some try to translate directly. This word goes to that word. And then maybe you have some reorderings. But then the reorderings, it turns out, would sometimes be helpful if you knew phrases and you understood the grammatical structure. So then people will actually use syntactic transfer. They say, well, I translate these phrases, and then I'll just kind of move the phrases around. Other people say, well, if I first understand the logic of the sentence, then I'll translate from the logic into just a surface form of another language. And that goes then all the way to an interlingua, like this sort of general space of all of languages. And you could then, once you have something in that kind of special interlingua language, you can easily translate it into lots of other kinds of languages. And so the question for you is, what do you think is the interlingua for deep learning that we'll use for almost everything? Vectors, that's right. For us, all of that will just be a list of vectors. And you won't understand this just yet in all its details as a figure, but here's a German sentence like, die Proteste waren am Wochenende eskaliert. And all of those words will be vectors, and then we'll describe them in deeper and deeper layers as vectors. And then the outputs, these vectors, will be all that we need to generate the English sentence, the protest escalated over the weekend. So everything will be just this list of vectors, and we can learn all of the complexity well, a lot of the complexity through an end-to-end trainable deep learning system. And this is indeed now what Google and a lot of other companies are using in their live translation systems. All right, so everything will be a vector. Hopefully everybody's excited. What that means in math is we'll use a lot of linear algebra, and we're going to take a lot of vector derivatives. So next lecture, we'll study how to compute these words, and we'll go on from there. Thanks, everybody.
You know anything about cs224n? Because they